Hello everybody, welcome to the Alkene review video. In this video we are going to pretty much cover everything from the bonding of an alkene, the nomenclature of this functional group, and obviously the reactivity and all the different reactions that we should know regarding alkenes. And then I'll do a subsequent video for alkynes. So this review video at this point should be just that, meant for review. In my mind, you should know all of this already, considering your exam is tomorrow, but I just wanted to give you a little bit of a summary of what we should know going into tomorrow. So without further ado, here we go. So again, this chapter is all about alkenes. Let me change the pen here. Let's make the sticker. Alkenes. Okay. And a generic alkene has the molecular formula of CnH2n. So, for example, if I wanted to do the 2-carbon, the ethylene, that would be C2H4. And what does that look like? Well, we have C double bond. And then with each carbon, we have 2 hydrogens. So this would be ethylene. Okay, and then we said earlier when we were talking about hybridization that the sigma bond in this carbon-carbon bond is a carbon sp2 orbital overlapping with another carbon sp2 orbital. And then, more interestingly, we saw that the pi bond is the result of the remaining unhybridized p orbitals. So that would be a carbon 2px with another carbon 2px. So the fact that we have this pi bond here makes this carbon-carbon double bond rigid, meaning cannot rotate, cannot freely rotate. This has a consequence in our reactions, as we'll see. But I guess a good depiction of this would be if I were to draw the orbital overlap of this ethylene molecule, where I'm just having generic R substituents. They could be protons, they could be other alkyl groups. We can imagine I'm just rotating this on its side, so rotation, 90 degrees, imagine. And let me just more specifically draw in the orbitals. So if I wanted to depict the p orbitals on its side, it would be like this. Okay, and now I'm going to do one further rotation, but now around the carbon-carbon bond. So I'm going to keep the carbon on the left constant, and I'm going to rotate just the carbon on the right. So that would look something like this. And the result of the p orbitals is something that looks like this. Is something that looks like that. So notice, if I rotate around a pi bond, a carbon-carbon pi bond, we're basically forcing one of the p orbitals to be out of plane, and therefore we don't have the p orbital overlap or the pi bond anymore. So my whole point is the feature of this p orbital overlap is what's preventing the free rotation. Okay, so just wanted to point that out. The pi bond is essentially broken by doing that. So let's also just talk briefly about nomenclature for alkenes. So let's just write that down. This is nomenclature. Your rules for alkane nomenclature still apply. We are going to number the longest carbon chain that contains the double bond to give the carbon atoms of that double bond the lowest possible number. And then we also always want to indicate the location of that double bond in the name. And then we also just name our branch substituents as we did before. So let me give you an example here. So I'm going to give you maybe a structure that looks like this. It's a big molecule here. So this guy, maybe I'll give you another one. Okay, so there's going to be a lot of things we want to talk about here. So the first thing is this idea of easy geometry. So remember that there are specific 3D orientations for alkenes with regards to the substituents around the carbon-carbon double bond. So specifically we're talking about, these substituents. Maybe I'll make this more clear. We're talking about like this substituent and this substituent and this one, and even the proton that's not explicitly there. So those are the substituents we're talking about, and that 3D orientation is what dictates this idea of easy geometry. So let's kind of just use my approach. So essentially what I do is I take a dashed line, put it through the double bond, and I fill in any substituents that I don't see. And then I take one carbon atom at a time, so for instance, this one carbon atom, and I decide the priority with respect to each side of the dashed line. So I'm thinking about the methyl versus the proton. Which one would be higher priority? Clearly the methyl, and then the proton. Then I consider the next, carbon atom, and then I think about, this substituent versus this substituent. I think it's pretty obvious that we go to carbon, to the eraser. We go from carbon to carbon, carbon, versus carbon to proton, proton. So this one's a little tricky, but the 1 is up here, and the 2 is down there. So let me just make some more room again. Okay, so now that we see that the 1s are on the same side of the dashed line and the 2s are on the same side, we would say that this one is a Z. Oh gosh, the pen keeps changing. This would be a Z alkene, or Z for same. Let's consider the other guy. So if I were to think this double bond, and I consider this carbon atom, I'm going to erase, this was for the last guy. Are we going to consider this carbon atom? Obviously, ethyl is more important than methyl. And I think this one's pretty obvious. We could see 1 versus the proton. So since the 1s are on opposite sides and so are the 2s, we would call this an E alkene. Okay, so that's number 1, is always determining what is Z and what is E. Now, we want to consider how to number this long parent carbon chain. So, if I were looking at this molecule, my guess is I would probably want to start from the right. And the reason that is I would encounter a carbon-carbon double bond, which is our new highest priority functional group, at 2 versus 1, 2, 3 on the left. Okay, so I think that's a little obvious. And again, we want the longest carbon chain, so it would make sense just to go all the way across and get an 8-carbon chain. Excuse me. So at the beginning of the name, we always indicate the position of the double bond, as well as the relative easy geometry. So at 2, we have an alkene, so we would put in parentheses 2. What type of alkene was that? Well, Z. There was also another one at 5. What type of alkene was that? Well, E. Close the parenthesis. And now we just would name this molecule just like we did with alkanes. So what substituents do we have? Well, we have a common one, isopropyl, with an I over here. And then we have a methyl over here with an M. So I would definitely name the isopropyl group first. So this would be 3-isopropyl hyphen 2-methyl. What's the longest carbon chain? Well, it's an oct. Okay. Where are the double bonds? So this is octa hyphen 2, 5, where the double bonds begin. And since there are 2 double bonds here, we would call this a diene. Okay, diene. And that's the name of this molecule. So this was probably the hardest one. We had easy geometry, common name substituents, as well as there being 2 double bonds present, so a diene. But we would expect you to be able to, name a molecule like this. Okay? And then let's do one cyclic example. Let me just get rid of this here. Let's do one cyclic example. So maybe I want to give you a structure that looks like this. So maybe some... I don't know, let me give you a hard one here. Okay, so let's do this one. Okay, so let me just make sure I want 7 carbons. So 1, 2, 3, 4, 5, 6, perfect. Okay, I have 7 carbons in this ring. Okay, let me put on some substituents here. Maybe something that looks like that. Okay, so quite a big molecule here. Okay, so just some things to keep in mind that with a cyclic structure, we're going to number the ring to give carbon atoms of the double bond 1 and 2. Okay, so we always want to start the numbering through a double bond. And we count in the direction, either clockwise or counterclockwise, to give the substituent encountered the smallest possible number. If obviously there's only one alkene in the ring, we don't really need to indicate the 1 position because it's just assumed to be at the 1 position. So let's kind of imagine this. So I see 2 double bonds. We can decide where we want to start here. So we have 2 kind of options. I could probably start 1, 2 and keep going counterclockwise. And I'll just do this in 2 different colors. Or we could start over here and go clockwise. We want to go through the double bond always. If I did the red numbering scheme, notice we have substituents at 1, 4, and 6. Oops. 1, 4, and 6. And if I did the green numbering pattern, it would be 1, 3, and 5. So that would be 4 plus 5 is 9. This would be 6 plus 4 plus 10, 11. This would be 11. Okay, so clearly we want to go with the green numbering scheme. Okay, so let me erase all this. Oh, actually, one more thing to consider here. Let me just bring those numbers back here. Okay, so first we wanted to see where our substituents were. So we have 1, 4, and 6 for the red, and then 1, 3, and 5 for the green. But then we also want to see the numbers of our double bond. So it looks like our double bond is at 1 and 4 versus 1 and 5. So that is actually a bigger, I guess, defining feature than the number or placement of substituents. We want to give our double bonds the lowest possible set of numbers. So in essence, I would actually do the red numbering scheme. So I did that mistake so that you guys can see what I'm talking about. So yes, we would normally think, where are my substituents? Let's give them all the lowest possible set of numbers, but the rule that's more important here is the double bonds getting the lowest possible set of numbers. So that would be the red numbering scheme. Okay, so I can't really erase in here, so I'm just going to leave it the way it is. But let's do that. So what are our common groups? Well, this is a tert-butyl, so by the B. This is a methyl by the M. And this is an ethyl with an E. So I think it's kind of obvious how to do this. This would be 6-tert-butyl, 4-ethyl, 1-methyl, cyclic structure. How many carbon atoms? 7, so hept, ta. There's 2 double bonds, so this is going to be a diene, but 1, 4 diene. Okay, notice there's no easy geometry in rings because obviously they're all inwards. There's no way to get easy geometry. They're all essentially Z on the same side in a ring. So anyway, that's an example of a cyclic structure and an acyclic structure for nomenclature. Definitely be able to do that. Okay, so let's talk about the reactions now of alkenes. So this is kind of the bread and butter of this chapter. So reactions of alkenes. Okay, and the first ones we're pretty much going to look at are these electrophilic addition reactions. So I would just call that electrophilic, additions. And of course, we'll look at some other ones such as redox reactions as well. So pi bonds can participate in chemical reactions as nucleophiles. So I just want you to kind of know that first. So I'm just going to draw a generic example of a double bond. If I just had a protic source perhaps present. This double bond, this pi bond, participates in the reaction as a nucleophile, meaning it has a source of electrons. You can imagine this is like a cloud of electrons. So nucleophile negative, attacking an electrophile, which is something positive. Okay, so we just wanted to see that. If you aren't sure why the double bond is a nucleophile, you can imagine the p orbitals that form the pi bond, and they are essentially a set of 2 more electrons in addition to the sigma bond that's already present, and they are farther away from the sigma skeleton than the actual hybrid orbital overlap. So essentially you can imagine like it's a flag kind of flying in the air saying, hey, I'm a source of electrons. Okay, so just wanted to point that out. These are nucleophiles. This pi bond is a nucleophile. Okay. And a fundamental reaction of alkenes is this idea of electrophilic addition. So again, let me just redraw this double bond with generic R groups. It could be a proton, it could be other alkyls, etc. And if I just have a reagent, I'm just going to call this E-Y, again, any generic reagent. You can imagine that across the double bond, you can add that reagent. So across, there are 2 carbon atoms, and notice that one fragment went to one carbon atom, the other fragment went to the other carbon atom. So examples of generic electrophiles that we'll see, reactions of alkenes are, for instance, hydrochloric acid, hydrobromic acid, We might see just a diatomic halogen like bromine. We could see something like BH3, borane, etc. And, if you've already, studied these reactions, you can see where we're going here. So I just wanted to point out a fundamental idea of this chapter is electrophilic addition to alkenes. Of course, there are other type of reactions we'll talk about as well. So reaction 1, we're going to talk about hydrohalogenation. And I think it's worth noting, you should know these names of the reaction, even though they're long. So this is the addition of a hydrogen and a halogen to an alkene. So what is the main reagent? Well, it's an HX reagent, okay? A proton, hydrogen, and X, meaning halogen. So hydrogen, halogen. Examples of that, obviously, are HCl and HBr. Okay? So let's see an example of this reaction mechanistically. So if I had a generic double bond here, so 2, and I had my hydrobromic acid, mechanistically it's always a source of the it's always the arrows coming from a source of electrons, which is our nucleophile, to a deficiency, which is our electrophile. If you can't obviously see the deficiency, you would imagine or go back to the dipole moments that we learned in chapter 1, and the halogen is definitely more electronegative than the proton, therefore creating a localized, a polarized environment such that the proton is the electrophile. And of course, we said that the double bond acts as a nucleophile. So mechanistically, it's our source to our sink, but hydrogen's only like one bond, so we exceed the octet, we must break that remaining sigma bond density, and it gets retained by the more electronegative atom, such as the bromine. The result is an intermediate. So this is an isolatable molecular species. More specifically, it is a carbocation. So what does this look like? Notice one of the carbon atoms got the hydrogen, so let me just kind of point that out. This carbon atom got that hydrogen. It's right here. We have an intermediate. This is called a carbocation. We're going to talk a lot about the stability of these in a second, so carbocation. And also from that last step, we generated bromine anion. Okay, so it makes sense that this nucleophile attacks that electrophile, that deficiency, and we've effectively added a hydrogen and a halogen across the double bond. This is hydrohalogenation. So the resulting structure should be something that looks like this. So this is a haloalkane, essentially, haloalkane, more specifically a bromoalkane, but I just want you to note that we can add a hydrogen and a halogen across a double bond in a reaction called hydrohalogenation. Okay, but we should probably talk a little bit about this intermediate, this carbocation. It is a reactive intermediate that is going to come up a lot throughout the course of Organic 1 and 2, so we should understand these intermediates and the relative stabilities and reactivities of these things. So we're going to do a brief aside on carbocation intermediates. Okay, so let's just kind of remember what the structure of this looks like. So again, I'm just going to bring back kind of this Lewis structure of a generic carbocation. Okay, so remember that this carbon is an sp3 carbon, but this carbon is an sp2 carbon. Okay, so a carbocation is sp2. But what does that look like in terms of an orbital diagram? This would look something like this. So all I'm doing is rotating. This was a rotation 90 degrees forward. So essentially like around that bond. And what does the p orbital look like? Well, remember there's this unhybridized empty, so I'm going to put a positive charge here, this empty p orbital. That is an electrophile, and we can essentially dump into this. We can add a source of a negative charge to this. So you can imagine a nucleophile can either attack from the front or it could attack from the bottom. That will have a dictation on our stereochemistry, which we'll see in another reaction. But I just wanted to point out what a carbocation's atomic orbital picture looks like. Molecular orbital picture looks like. And this is what it is. So there is relative stabilities of carbocation, and I think I'm just going to first introduce the trend, and then we'll understand why that trend is the way it is. So essentially, a structure that looks like this is what we call a tertiary carbocation, and that is the most stable. It has similar stability to what we call a benzylic carbocation. So this is a carbocation directly outside of a benzene ring. So benzylic carbocation, those are really, really stable. So those have equivalent stability in my opinion. Then the next one would be a secondary. So there's a proton here. A secondary carbocation, which is a little bit better than what we call allylic, so directly adjacent to a double bond. This is allylic carbocation. Okay, and that is way, way better than what we call a primary. Excuse me. A primary carbocation. Oops. And of course, that's way better than just the generic methyl carbocation. So clearly it seems like substitution plays a role. And also, these double bonds of a benzene ring or the allylic structure seem to also play a role. So we could probably see that resonance would also play a role here. So this is the generic trend. Let's kind of understand this idea of carbocation stability. Okay, so maybe this part of the notes will just be understanding carbocation stability. Okay. So the first thing is resonance stabilizes charge, as we've seen before. So resonance stabilizes charge. So essentially, if I had this molecule, this carbocation, and I have this carbocation, Y is the primary allylic on the right. This is primary allylic, better than the generic primary. Well, through a resonance lens, you could see that that double bond can be pushed to the right, that deficiency. We get an alternative resonance structure, still primary allylic though, but the fact that I can spread this charge over the skeleton of the entire molecule is a stabilizing feature which makes this, essentially not as reactive. Okay, so we can actually isolate this intermediate, the primary allylic, better than the primary. So that would be a rationale, resonance stabilization. I can give you another example of that. So what if I gave you potentially this secondary carbocation and then this other secondary carbocation? So essentially, this oxygen heteroatom being adjacent to the secondary deficiency allows us to donate, let me actually change color here, donate electron density into that deficiency. We get an alternative structure. Looks like this. And of course, yes, the positive charge on the oxygen is not great. But the fact that we could stabilize partially by donating negative charge into that deficiency overrides the fact that I'm getting a positive charge on the oxygen. So the secondary with the oxygen, I would just call this secondary resonance, is more stable. Okay, so again, the carbocation on the right is more stable. So resonance is a good feature. It doesn't have to just be, with a pi bond doing resonance. We could also have heteroatoms like the oxygens or the nitrogens also play a role. Okay, another trend I want to talk about quickly is this idea of hyperconjugation. So hyperconjugation, fancy word, but it'll make sense in a second. So hyperconjugation applies to all carbocations. So again, let me just bring back this this molecular picture here of what a carbocation intermediate looks like. Okay, so remember, a carbocation has a unhybridized empty p orbital, so with a positive charge. Okay, so you could imagine that adjacent orbitals could potentially lean over and fill this deficiency. So what do I mean by that? Let's kind of copy this same image. I don't really care about these protons for right now, but I want to talk to you about this bond up top. So I'm going to circle this in another color, this bond. So this carbon-hydrogen bond, in terms of looking at orbital picture, is really an sp2 carbon hybrid orbital overlapping with a hydrogen 1s orbital. Okay, so I'm just going to bring that back. Remember, this is what is really going on here, okay? And we can imagine that on the other side, let's just reproduce that p orbital, empty, that we just talked about. Okay, and obviously we could fill everything else in. So you could imagine at any given point, this bond, this carbon sp2 hydrogen 1s bond, could lean over slightly and donate some electron density into that empty p orbital. This donation into this empty p orbital allows it to be more stabilized. Okay, so you can now imagine why we saw tertiary is greater than secondary, which is greater than primary, which is greater than methyl, just based on sheer statistics of how many orbitals are likely to lean over. You can imagine with a tertiary carbocation, you have 3 possible groups that could lean over. Actually, you have 9 possible groups, 9 CH bonds here. There's 3 on each of these. 9 CH bonds on all of these carbons that could potentially lean over and stabilize that deficiency. But if you had a secondary, you could imagine there is a total of 6 CH bonds here and here. And then for primary, something like that, you can imagine there's 3 CH bonds. So this just comes down to the idea of how many, bond orbitals can lean over, and clearly the more substituted, the more likely you are to do that. Okay, so that is that trend. I also want to briefly introduce this idea of inductive effect with carbocations, so induction. So if you recall, back to acid-base chemistry, if I had generic phenol, and I had parafluorophenol, so something that looks like this, and we were talking about the pKa's here. The pKa of a phenol is typically around 10, and we could say that the pKa of this fluorinated version maybe is around 4. So there's something about this halogen being present that allows for the acidity to be increased. So remember, if we were treating this as an acid-base problem, a generic base, such as B-, could come in and deprotonate that proton and make a negative charge, and we would ask ourselves how that negative charge is stabilized. Not only is there a resonance effect with this double bond here, we could push these around, but this halogen being present allows an inductive pull via a dipole moment. So we said in terms of acid-base chemistry, induction is good. What we're going to see right now with carbocations is the exact opposite trend. Induction is not a stabilizing feature, but rather a destabilizing feature. So let's kind of see that in action here. So if I were to give you 2 different structures versus this, so 2 different secondaries. I'm going to say this is a secondary induction. This is generic secondary. You can imagine that this carbocation is already deficient. But what does the halogen being present do? Well, it pulls, via the sigma skeleton, electron density away from an already deficient center. So essentially, you're making this even more deficient, which is bad, considering there is a perfectly fine secondary carbocation here without a halogen. So here, induction is a destabilizing feature. I think that's important to point out, okay? So with that being said, I think we're ready to jump into our reactions a little bit more. So I want to bring back this idea of hydrohalogenation now with this idea of a carbocation being present, okay? So as we can see, carbocations have this empty p orbital, okay? There's a consequence that I alluded to earlier, that a nucleophile could either arbitrarily attack from the front or the back. So you can see we're going to talk about some stereochemical considerations here, okay? And as well, maybe we'll talk a little bit about thermodynamics and the rates of reactions. Those are kinetics. Okay, so another page of the notes here. So we're going to just talk about quickly the stereochemical considerations. So we're going to bring back this idea of hydrohalogenation. Continued. And more specifically, we're going to talk about stereochemistry to consider. Okay, so again, I'm going to bring back just a generic example of this reaction. We have an alkene. We have our hydrogen and bromine reagent. This is hydrobromic acid. We can imagine that we are going to add across that double bond such that we get a proton and a bromine. But we have to consider, did we generate a new chiral center? We absolutely did over here. This is an sp3 hybridized carbon with 4 different substituent. Okay, so maybe you just remember I need to like look at all my carbon atoms and see did I generate a stereocenter. You can do that, but I do want to bring back this idea of this molecular orbital picture. So if you were to draw, you know, essentially I'm going to rotate this 90 degrees, but if I were to draw, excuse me, I'm getting a little ahead of myself here. If I were to draw mechanistically how this is clicking, the pi bond grabs the electrophile, we exceed the octet, and we generate a carbocation. What does that look like? That looks like this structure. If I wanted to rotate 90 degrees forward, that would look like this. How do I do this here? And this is the unhybridized p orbital. That's empty, okay? That bromine that we generated from that last mechanistic step can either approach in pathway A or pathway B. And if it did so, let me show you the 2 different structures. If it attached to pathway A, it's attaching from the front face. So essentially that would be versus pathway B that attaches from the back face here. Notice 2 very different stereoisomers, okay? So essentially you could just go to the end and imagine, okay, this attached wedge and dash, or you could actually rotate the molecule and see how the relative pathways, you know, evolve. So again, we did have 2 enantiomers present here, so we would call these enantiomers. You could say that both of these form an equal mixture, so 50-50 mixture of both enantiomers is something called a racemic mixture. Oh, the pen is messing up here. Racemic mixture. And another thing you could say on the test is you could put parentheses plus/minus to indicate that you know that there are 50-50 quantities of these. Okay, now maybe we'll just briefly introduce this idea of a reaction coordinate diagram with this reaction. So again, this is just a subset of hydrohalogenation. Again, let's just draw this main reaction again, mechanistically. Whenever you want to answer questions about a reaction coordinate diagram, it's helpful to draw the full mechanistic picture. Okay, and now we want to fill in a reaction coordinate diagram. So what does this look like? So remember reaction coordinate diagrams, this is back to Gen Chem. The y-axis is energy, the x-axis is time or reaction coordinate. So essentially we start with some energy level, and that is where our starting materials are. We essentially always encounter some sort of energetic barrier to do the first step of the reaction. But the result of the first step of the reaction is some sort of intermediate that is always higher in energy than the starting material. That makes sense. Intermediates are always higher in energy. And if you didn't necessarily know that, you would imagine that a charged species is worse than a neutral species. So the first intermediate's energy well should be higher than the starting materials. Okay, so this would be like an intermediate, specifically a carbocation. But it looks like there's one more transformation that happens. There's probably a subsequent energy barrier to that. And then ultimately we will end with an energy level, well, for our product that is more stable than the starting materials. That's the whole reason we form bonds, is that the product is a more stable structure than the starting material. However, the pathway may be a little bit difficult to get there. So 2 things I want to point out. The first arrow has an energetic barrier called EA1, and the second one has an energetic barrier called EA2, so I'll just fill that in here. The energetic barrier is defined as the energy distance between the top of the curve and the beginning of the curve. This would be EA1, and then the next one would be EA2. Notice EA1 is much, much greater than EA2. Okay? Specifically, the intermediate well right here would refer to this carbocation structure. Okay? And the product structure should be this Markovnikov addition product. And then we obviously know what our starting materials were. Something that looks like that. Okay, so be ready to fill in, molecules and answer questions based off of an energy diagram. I don't think it's too complicated. I think we just need to be able to draw out a full mechanism and then piece by piece, write a graph about it. Okay, so I think I'm going to take a quick break before I talk about regioselectivity. Okay, so we just basically touched on this idea of stereochemistry, this idea of a rate of a reaction or the kinetics of a reaction with an energy level diagram. And finally, I want to just talk about this idea of regioselectivity and Markovnikov's role with hydrohalogenation. So again, another piece of this is regiochemistry. More specifically, Markovnikov's role. Okay, so essentially, if I were to give you a generic reaction like this, I had my hydrobromic acid, and I wanted you to draw the mechanism, it would be the source of electrons from our nucleophile attacking an electrophile. We generate a carbocation, but now the question is, I could generate the carbocation at the secondary position versus the primary position. And we kind of already alluded to the fact that hyperconjugation is a rationale for why the secondary carbocation is a better structure. But this has something to do, this is where the regiochemistry gets involved. The choice of where the hydrogen atom goes on a carbon-carbon double bond. Notice there's two potential sites of a carbon-carbon double bond. This idea of forming a secondary carbocation preferentially is a regiochemical situation or circumstance, where the proton specifically goes to the less substituted side. Okay, so the proton is at the less substituted side. And then as a consequence, the bromine from the next step is going to go on the more substituted side. To observe this feature happening in a electrophilic addition reaction of a double bond is the definition of regiochemistry or Markovnikov's rule here. So specifically, if we think about the product that results from a secondary carbocation, we would call this the major or Markovnikov product, because it's following Markovnikov's rule, where the proton goes to the less substituted side and the main electrophile, the main nucleophile, the bromine, goes onto the less substituted side. More substituted side. And then if we had the primary carbocation case, the bromine adding at that specific intermediate would mean this is the minor product, this is the anti-Markovnikov product. Okay, so a regioselective reaction overall is just an addition reaction in which one or two or more possible products can form, and there's preference to, one versus the other. Okay, and again, this idea of hydrohalogenation is definitely a regioselective reaction. Okay, so I think this is a good point to start talking about other reactions. So we saw hydrohalogenation in its entirety, so let's just review. It was a situation where the nucleophile, which is our pi bond, attacks the proton of either hydrobromic or hydrochloric acid, generating a carbocation intermediate that is either attacked from the front or the back face by a halogen anion, whether that be a bromine or chlorine. A stereocenter could result, and specifically there are stereoisomers that you would have to consider. And I think that is good. Okay, good. I like that. That's enough. Let's move on to reaction number 2. So this is alkene hydration. Okay, so reaction 2. This is still an electrophilic addition reaction to an alkene. So maybe I have a generic structure that looks like this. I don't care what my substituents are. They could be protons, they could be other alkyl groups. The difference here is I'm going to have water as my main reagent and some sort of acid catalyst. So I'm just going to put H+, and then cat in parentheses to show you. And then what happens is we are going to have OH and H add across that double bond, okay? So this is clearly an electrophilic addition. We are adding two different groups, the OH fragment and the H fragment from water across that space. Okay, what are examples of this H plus catalyst? Those can be HCl, sulfuric acid, any strong acid essentially, so a lot more. But these are just some examples, okay? So let's see a full mechanism of this. I did just want to point out that this is a functional group you should recognize. A COH group is an alcohol. So we have now officially seen alkene to a haloalkane. This is now alkene to an alcohol. Okay, so mechanistically, how does this work? So I gave you this example. So water, hydrochloric acid. Whenever you see two reagents over a reaction arrow, you always assume that those two things are going to react first before they touch your substrate. We know that this is a dynamic equilibrium where we're going to create hydronium and chlorine anion. And hydronium is the main reagent that I want you to be aware of that's interacting with this double bond, this alkene. Okay, so I need some more space, so I'm going to move all this up here. So what does this look like? So if I have this starting material substrate and I have hydronium, you can imagine that our source, our nucleophile, is going to grab a proton, and we exceed the octet, so that sigma bond density is retained by the oxygen atom. We have a regioselective choice here where the proton is going to go preferentially to the less substituted side to form a more stable carbocation intermediate, a secondary carbocation intermediate, and the result was water from that last mechanistic step. You could imagine that the lone pair of the oxygen is a source of electrons that acts as a nucleophile that attacks that electrophile. At this point, remember that p orbital is unhybridized, and we can either attack from the front or the back. So we have our stereochemical considerations kind of emerging here, where we have either a wedged alcohol. Oh, excuse me, I'm skipping. A wedged protonated water, or a dash protonated water. But for those that know their stereochemistry pretty well, you can imagine that this is really not a stereocenter because the substituents on the left and the right are the same. So for all intents and purposes, we don't really need to think about the wedge dash orientation for this problem, but I just wanted to point out where the stereochemistry emerges from. Once we have the protonated water add in, we just want to make this a neutral product, so you could assume that there is excess water around. That forms, let me change color here, that forms the neutral alcohol, a structure that looks like this. And more specifically, we also regenerated from right here, we regenerated our hydronium, which is the definition of a catalyst. It is regenerated in the course of a mechanism, okay, but not actually used up in its entirety. So anyway, this was another electrophilic addition reaction where we added water across the double bond such that we have an alcohol form. Keep in mind you can get stereocenters that you need to consider, and more specifically, you know that this was a regiospecific Markovnikov addition reaction that has carbocations where rearrangements are possible, okay? So, what's another example of that? I think that might be good for acid catalyzed hydration. Maybe I'll just do an example of a rearrangement. So, one example of this could be okay, so you imagine water and sulfuric acid react so that the main reagent is hydronium. Just showed that on the last page. The nucleophile is this pi bond that grabs a proton, and that electron density is retained by the water, the oxygen. The result is a carbocation outside of the cyclic structure, and obviously water. But here we see that we can do a ring expansion from a 5-membered ring to a 6-membered ring. So we would cut that carbon-carbon bond, swivel it over, and essentially you get a 6-membered ring. For your purposes of your class, we're only going to assume one rearrangement. In actuality, this breaks down. Of course, we get a much more complex mixture of products, but you either just do the ring expansion or you do an alkyl or hydride shift. You're not going to do both in tandem. So this is a secondary carbocation here where water now can add in. This is where the stereochemical consideration emerges. You can imagine that be either from the top face or the bottom face, but we would just get the structure that looks like this. And finally, you can imagine there's excess water around to form the neutral alcohol. Okay, so the result is a structure with two stereocenters, and we would have to consider 4 stereoisomers for your product. You could not write plus minus because there's also diastereomers in that. The plus minus is exclusively reserved for 2 equal mixtures of the enantiomers, the 50-50 enantiomers. This is diastereomers also involved in the reaction mixture. So you would imagine that they're really, on the test, you would have to write wedge, wedge. You would have to do dash, dash, wedge, dash, and dash, wedge. These are all the answers for that one question, okay? Just keep all that in mind, okay? Now we're going to talk about maybe another type of reaction we have here. What's a good one we could do? We're going to talk about halogens going across the double bond. So reaction 3, halogenation. So just to keep in mind where we are, we saw hydrohalogenation. That was a HBr reagent or an HCl reagent. We saw hydration. We saw water and acid. But now we're going to see just a plain halogen go across. So again, if I were to bring back this generic example, X2 denotes some sort of halogen. Typically, we see a solvent associated with this. I'm going to draw this in a very specific way. Okay, so notice we are adding halogens across the double bond. We are adding halogens across the carbon-carbon double bond, more specifically in an arrangement called the anti-arrangement. Okay, so again, just some other things to point out here. The X2 is either diatomic bromine or diatomic chlorine, and often the solvent is either chloroform or DCM. You might see it as DCM. You might see it as methylene chloride. These are all the same. Sometimes you even see carbon tetrachloride. These are all inert solvents. They just help the alkene and the actual halogen, dissolve and approach each other nicely on paper. So, how does this work mechanistically? So this is pretty interesting. This is another stereospecific reaction. So stereospecific. I think this is actually this is the first stereospecific reaction we're going to see. So before we saw regiospecific, where we preferentially had some sort of nucleophile add to the more substituted side, like water, to form an alcohol. That is a regioselective choice here. In this reaction, we're going to have a stereospecific choice, where we see that the 3D orientation of this main electrophile is going to change in space. Okay, so here's an example of a mechanism for this. So if I had a cyclic structure, perhaps like this, and I had bromine, mechanistically this is how it works. We have a source that attacks our electrophile. We exceed the octet, and we get a structure that looks like this. Okay, and obviously the bromine anion from before. The other lone pairs on this bromine can lean over and stabilize that carbocation to form what we call a halonium bridge intermediate. It's a 3-membered bridge, highly strained, positive charge on a halogen, not very stable, okay? But this is called a bromonium, or more specifically, a halonium bridged intermediate. That dictates the stereochemistry. Specifically, you can imagine that, again, with this pi bond, that bridge could have formed from the front face of the pi bond, or the bridge could have formed from the back face of the pi bond initially. So you need to be aware that this is really what's happening. Both bridged intermediates exist, and there's a different consequence for having the bromine attack both bridges. So for the wedged example, the top face of this molecule is already sterically hindered. Therefore, the bromine is preferentially going to attack from behind, breaking open that bridge, and the result of that mechanistic transformation would be something that looks like that. The bromine came in on the dash, which forced the present one to swivel over on the wedged. Okay, so that is the first anti or stereospecific arrangement we have seen. And likewise, if we had this dashed structure, we would imagine that the bromine has to attack from the front face, swiveling that bridged, halonium open as a dash. So the structure would look like this. Notice two different anti-products. These are not the same. These are enantiomers. You can't flip or rotate, such that these are the same. They're a 50-50 mixture. You could write plus minus. You could also say racemic. These are all the same thing. But notice the halogens are on opposite stereochemical configurations, wedges and dashes. Okay, so this was a stereochemical reaction. Stereospecific reaction here. Okay, hope that wasn't too bad. Let's see if there's anything else I can talk to you about this one. No, I think that's good. Let's talk about halohydrin synthesis. Excuse me, I'm a little sick, so you can hear I'm congested, and it's hard to get the words out today. But anyway, that was reaction 3. We're going to talk about reaction 4. Halohydrin synthesis. So this is a subtle variation of what we just saw above. So instead of there being an inert solvent like chloroform, carbon tetrachloride, or DCM, we're going to replace it with water. So again, generic same diatomic halogens, X2, but now we're going to see water replace the DCM, chloroform, or carbon tetrachloride we saw before. So again, we're going to still have this idea of anti-addition, but so specifically, we're going to see something that looks like this. And if you're wondering how this is anti, again, I just want you to imagine this is a Newman projection. That's why I'm drawing it these ways. If I'm drawing it from that orientation, you could see how the front and back groups, the OH and the X, are opposite or anti from each other. Okay, so that's why I'm drawing it this very specific way. So notice before we had X and X trans like that, or anti. I'm just going to highlight this another color. Where is that? Maybe on the last page. Notice we had the halogens, trans or anti from each other. Now the halogen is anti or trans from an alcohol. So an alcohol and a halogen being adjacent to each other is a halo from the halogen part, hydrin part, so halohydrin. Okay, that's what that functional group is. Okay, so always the halogen ends up on the less substituted carbon, and the alcohol ends up on the more substituted carbon. As well, the orientation of the halogen and the alcohol are anti. So this is our first reaction that is both stereospecific and regiospecific. The alcohol will always add to the more substituted side, and the halogen and the alcohol will always be anti to each other. So those are two different types of things we need to consider. Okay. So let's take this example, for instance. Okay, so the first thing is we're going to have the halogen form a halonium intermediate. So I think that's pretty obvious. This is kind of from the last reaction we just showed. So the pi bond comes here. We break the bromine. We get a structure that looks like this. And don't forget that the lone pairs really come over, and we get this kind of halonium intermediate. Okay. So I'm going to do a quick solid for you, and I'm going to rotate this molecule a little bit. So it would be easier for me to show the halonium bridged in plane, and I'm just rotating the methyls such that you can see them nicely. So, how should I draw that? I guess into the board. Something like that. Okay? So from this halonium intermediate picture, we can see that water, not the other halogen, not the bromine anion that we generated from up here. This is not as nucleophilic as this water. So water is the amine reagent in the next step. Now, there's a regioselective choice. We could either attack at the more substituted position, pathway A, or we could attack at the less substituted position, pathway B. And we're going to attack at the more substituted position because a more stable intermediate results there. So let me just prove that to you. So right now we have a positive on a bromine. That is horrible. So if I were to consider a resonance picture here, and I break that bond, this is not part of the mechanism, this is just me proving this to you, we would get a tertiary carbocation. If I were to break the other way, I get a secondary carbocation. Since the tertiary is more stable, this is the intermediate that exists more likely in the resonance hybrid. So it would make sense that the negative charge thing, the water, wants to attack that intermediate. Okay? So this is the regiochemical origin here, where water is always going to attack the more substituted side. I just wanted to prove all that to you. Okay, so let's kind of see that from the main mechanism that we drew. Water is going to attack here, forcing the bromine bridge over. The result is a structure that looks like this. Excuse me. Other way. And finally, you could assume that there's excess water hanging out, such that you form the neutral halohydrin. I'm running out of space here. Let's go on to the next page. It would be a structure. It looks like, oh, we're losing it. Quality, HO, 3R. Okay, cool. Okay, halohydrin. Okay, so again, this was regiospecific in the sense that water's at the more substituted position, and it's also stereospecific because the alcohol and the halogen component are anti or trans to each other. Okay, so again, nothing really crazy here. Just keep in mind all these nuances. Okay, of course, we have other variations. Instead of it being water as the main reagent, I could replace this with some sort of alcohol. So, for instance, like methanol, and the result would be like a haloether synthesis. Okay, you would imagine that you have the methoxy group go on here. Instead of OH, it would be OCH3, and you formed a haloether. Okay, so just some subtle variations, but again, similar structure reflects similar reactivity. Okay, now we're going to go through some weird nuanced reactions that really aren't used in practice, but I think they are still worth understanding. So the first one we're going to talk about is oxymercuration, demercuration. So I guess we'll call that 5. Okay, so we're going to talk about some more weird, I guess, or nuanced reactions of alkenes. I'll just preface that these reactions are not really used in practice, but they can be done and they do work. But of course, this is kind of just like the baseline of organic chemistry, kind of at the undergraduate level across the board. They always teach these reactions, but these aren't really common. But we should still understand what's going on here. So I guess we'll pick up where we left off, reaction 5. We're going to call this oxymercuration, demercuration. Okay, reaction, I guess. And the reagents are pretty specific, but essentially, before we get into the actual mechanism, this is an alternative to alkene hydration. So, alternative to alkene hydration. So that was the water and acid reaction. So we basically do the same result. It is regiospecific. We are going to form an alcohol at the more substituted position. This is following Markov-Nikov's rule. However, there are no carbocation intermediates. Let me write that all down. So this is Markov-Nikov, or that's basically saying regioselective addition. But the feature here is there's no carbocation rearrangements. You could imagine why we would ask this on a test because there could potentially be a structure that looks like this, that is screaming ring expansion. But if I did, the conditions that we're about to describe, the oxymercuration, demercuration, you would simply just have the alcohol add at the more substitute position without the ring expansion because there was no carbocation intermediate. So I'm just going to show that up front because that's the whole reason why this reaction is taught, is to basically show you that there's an alternative that you can add alcohols without going through that, expansion pathway. So, again, let me just show a generic scheme here. If I had, generic structure that looks like that, R is anything, there's always this two-step process. So the first one is this reagent called mercuric acetate. So two acetate molecules sandwiched between, a mercury, a metal, an inert solvent such as THF, and water. And then in step 2, there's a reduction. So sodium borohydride and water as well. The result is an alcohol that is at the more substituted position. Therefore, it's reach selective, and there are no rearrangements possible. So that's kind of a generic scheme. What does mercuric acetate look like? I just always like to show that to kids. So an acetate molecule looks like that. Mercury is 2+, and there's another one to obviously neutralize that structure. So that's mercuric acetate. What does sodium borohydride look like? Well, we have sodium, and the borohydride fragment is a tetravalent boron. That's a negative. So that's sodium borohydride. This is a reducing agent. This is a source of hydride. Okay, so just be aware of these structures and what's going on here. So let's kind of show the mechanism. We don't teach the full two-step process, but I'll show you as much as we do expect you to know. So essentially, we have this double bond, and we have mercuric acetate. This is a concerted mechanism where the nucleophile pi bond attacks the mercury, breaks one of the acetate molecules open, essentially reforming that halonium bridge like we saw before. But we typically show the mercury also coming back to form the bridge. So that would be a structure that looks like that. And then you can imagine water, just like we saw with the halohydrin synthesis, preferentially attacks the more substituted position, so the tertiary over here, breaking open the ring, and the result is a structure that looks like this. So this is, not yet. We have the protonated water molecule, and we just imagine there's excess water to form the neutral alcohol. So essentially this is the product from step 1. Notice the OH, the alcohol, and the mercury group are anti from one another. Product of step 1. In step 2, the sodium borohydride, so I'm going to recopy that structure over here. In step 2, the sodium borohydride is the source of hydride. So source of, when I say that, that's that. Source of hydride that essentially just displaces this whole kind of group. So, I'm going to show the mechanism. We don't necessarily expect you to know this yet, but I think it's pretty self-explanatory. This hydride comes here and kicks out the mercury. So the result is a Markovnikov alcohol. So you can imagine, without seeing, the full mechanistic picture, I would imaginably go from here, and I would say, okay, Markovnikov addition, no rearrangements, alcohol, done, which is essentially this. You just get rid of the proton. Okay, so that is oxymercuration, demercuration. Notice there was no rearrangements possible. So I guess, just to bring this idea of why we teach this reaction into focus, let's show you this example in 2 different pathways. Okay, so for step 1, this is acid catalyzed hydration. You can imagine hydronium is the main reagent. We form a carbocation at the more substituted or the secondary position. Oh, but we are primed for a 1,2 alkyl shift. So we have a structure that looks like this tertiary carbocation, where water will eventually attack. I'm skipping a whole bunch of mechanistic steps, but this is the product of that pathway, this alcohol. For this structure, we do not have any rearrangements, so you can imagine that we have a no carbocation and the alcohol going on the Markovnikov secondary position. So notice very different products, still both alcohols, but two different constitutional isomers here based off of the intermediate we decide to go through, okay? That's the reason we teach this. Of course, if there's a Markovnikov, version of this, there's probably an anti-Markovnikov version of this. So the first one was oxymercuration, demercuration, which was Markovnikov addition. We saw that over here. Now we're going to do the anti-Markovnikov addition. So this is going to be reaction 6. This is hydroboration oxidation. Okay, so again, a generic structure maybe would look like this. Okay, and just without even putting the reagents, if I'm telling you this is anti-Markovnikov, you would imagine that we are going to get an alcohol at the less substituted position, okay? And the reagents that do that is borane and THF, an inert solvent, and step 2, sodium hydroxide and hydrogen peroxide, okay? So again, mechanistically, actually, before I talk about the mechanism, let's just show the Lewis structures of these things. Borane is a trivalent boron with 3 hydrogens, and it is neutral. Okay, even though it's deficient, boron is one of those exceptions to the octet where it's okay or perfectly happy being electron deficient. And hydrogen peroxide, just bring that out, looks like this. Okay, those are the 2 things here. Now, in terms of the mechanism is quite interesting. There's a reason we're using borane. So if I were to not get rid of here, let's not do the R, let's just do this. Okay, so I'd want to draw borane. Okay, so borane has a sterically hindered side and a less sterically hindered side. What do I mean by that? Well, 2 of the protons on one side of the borane is what I call the BH2 fragment. This is the steric side, BH2. And then there's the hydrogen on the left side. So the right side of the molecule is going to align such that it is sterically away from the bulkier side of the alkene. So between this carbon and this carbon, which one is bulkier? Well, the one on the left is clearly bulkier. So the BH2 approaches in such a way that the BH2 is towards the right of the molecule and the hydrogen is on the left. This is in comparison to that orientation, that approach, where the BH2 aligns with the methyl. We don't want that. We want the BH2 to align with the opposite side of the methyl, essentially, over here. It's a steric argument. So mechanistically, how does this work? It's another concerted mechanism. The pi bond is the source that hits the deficient boron, the electrophile. We exceed the octet, so this hydrogen atom sigma bonded density kind of also comes back around at the same time. Notice, this is a stereospecific and regiospecific reaction. Regiospecific in the sense of the BH2 is going to the less sterically hindered side always, but stereospecific in the sense that it's a concerted mechanism. It's a concerted mechanism, meaning that the BH2 and the H group get added at the same time. So if the BH2 is coming on a dash, the hydrogen's also coming on a dash, and vice versa. So the result of this step, product of step 1, would be the BH2 at the the sterically unhindered side, and the hydrogen is at the sterically hindered side. So at this point, this is a regiospecific reaction. Borane is BH2 fragment always on the less sterically hindered side, hydrogen on the more sterically hindered side, and then more specifically, it's stereospecific, but stereospecific in the sense that it is syn addition. So we saw anti-addition with the halohydrin and the halogenation reactions. This is the opposite, where they're going to add not opposite, but the same phase. That's syn addition. Okay, so I guess I should point that out. The H and the BH2 add same orientation, meaning both wedge-wedge or both dash-dash. Okay, so that's the product of step 1. Product of step 1. Now, in terms of step 2, the mechanism isn't totally covered, but you can imagine there is a source of OH, so it would just displace the BH2, so we don't teach that mechanism, but you can just imagine the BH2 goes away, and you can see that we have, if we're comparing this to the starting material, we have anti-Markovnikov alcohol addition with no rearrangements because there's no carbocations. Okay, so that is hydroboration, oxidation. Okay, and I think maybe I could just show you one more example just to piece that all together. One more example of this. If I were to give you the structure in hydroboration conditions, you would immediately look at the less sterically hindered side. You would say, okay, that's more sterically hindered, that's less sterically hindered. There's no rearrangements possible because there's no carbocations done. Okay, so that is hydroboration. We have a few more reactions to go. Okay, and now we're going to wrap up with the final oxidation reductions of alkenes. So I think before we were on reaction 6, let's talk reaction 7. Okay, so just off the bat, these are going to be redox or oxidation reduction of alkenes. And I just wanted to point out, we remember this idea of like oil rig, maybe back from Gen Chem, where oxidation is the loss of electrons and reduction is the gaining of electrons. And yes, that is still true in organic chemistry, but we do have a different definition. So in organic chemistry, oxidation equals the addition of an oxygen atom to a carbon and the removal of a hydrogen from a carbon. So you can see that if oxidation is the loss of electrons, the removal of the hydrogen from a carbon satisfies that component. But the new organic chemistry part is we're really going to see a new oxygen atom emerge, hence oxidation. Reduction is the opposite. So for reduction, it is the removal of oxygen from a carbon or the addition of a hydrogen to a carbon. Okay? So the addition of a hydrogen to a carbon is the gaining of electron component. The new organic component is the removal of the oxygen. Okay? So in the context of an alkene, there will be ways to take an alkene to go to a structure that looks like this. We are putting clearly, oxygen atoms on this molecule, so this would be oxidation. But there's also ways that we can get rid of that and maybe go back here and give it hydrogen atoms. So we're adding hydrogen atoms, so that would be a reduction. Okay, so we're going to play with those reactions right now, redox. Okay, so the first one is going to be something called syndiol synthesis. So I guess this is reaction 6, I think, or 7. Okay, so 7. Syndiol synthesis. So if we break that word apart, it would be same orientation, diol forming. Okay, so what does this look like? A generic alkene. We have osmium tetroxide, hydrogen peroxide, and water. And what happens? Well, across that double bond, we form 2 alcohols, so the diol. And more specifically, these two are going to be syn with respect to each other. Syn orientation. So this is another stereospecific reaction. Okay? So, what does osmium tetroxide look like? It's a really weird structure, but you'll never forget it. It has a center osmium that is allowed to take on, I think it's 4, 8. It's 16 total valence electrons. That's a lot, double the octet. And let's just show you kind of how this works mechanistically. So if I gave you this cis, alkene, and I gave you osmium tetroxide, hydrogen peroxide, and water, the result is a structure that looks like this. Notice they're both wedges, or you could do the both dash, but notice this would be a meso compound. These would be equivalent essentially. But essentially notice that they have 2 alcohols across the double bond and they are on the same orientation. How does this work mechanistically? So the mechanism for this, let me show you another example. So we don't expect you to know the full mechanism, but pieces are definitely expected. But here, the pi bond is going to attack an oxygen. We can see the octet. So a double bond goes down, and forcing this pi bond out. It's a very weird mechanism, but it's concerted. It all happens at once. And you should be able, we would expect you to get to this intermediate. So imagine, if we're approaching, the osmium tetroxide is approaching from the wedge, it would force this methyl on a dash. So I just wanted to point that out. So oxygen, osmium, oxygen, osmium. So you should be able to get to that intermediate. And likewise, if the osmium approached from the back face, that methyl would have been on a wedge. And you have these two intermediates. The water and the hydrogen peroxide is just, you can imagine, hydrolysis of this really strained bond. And we don't teach that part of the mechanism, but you could see where the diol arises. This is oxidation because we gained oxygen atoms to these carbon bonds. Okay, and then this one would be that and that. Okay, so these would be the two enantiomers that you would have to draw on the test. This cyclic structure in the middle is called a cyclic osmate. Just be familiar with that terminology. We would expect you maybe to even draw that ring. Okay, so that is that. Let's talk about another oxidation. This is ozonolysis. So this would be reaction 8. Ozonolysis. Okay, so it's essentially throwing ozone on these molecules. And if I just showed a generic double bond again, and the reagents are going to be always step 1, ozone, O3. Step 2, this reagent called dimethyl sulfide. So you might see it as CH3-2S or sometimes DMS, just dimethyl sulfide. Those are some equivalent ways of doing that. The mechanism is not covered whatsoever, so that's nice. You just need to know that when you see this, you essentially want to cut down the double bond, and you just put a carbonyl where you cut. So notice the left fragment here, is here, and now the right fragment here is here, but where you cut the double bond, you put an oxygen. Okay, so what is the result? Well, we can form aldehydes or ketones from these alkenes. Okay, so maybe I'll write that in. Could be aldehyde or ketone. I should say and or ketone. Okay, so let me give you another example of that. So that would be a structure that looks maybe like this. And I said ozone, DMS. What I would just do is cut right here, keep the fragments close together. You still draw the double bond of each fragment, but since you cut there, just remember to put an oxygen. Okay, so you can see how I'm cutting and just putting oxygens in between. And notice that this is an aldehyde, and this is a ketone. Okay, so that's just one interesting thing. There is also a ring opening version of this, so I just want you to see it. It's almost always asked on an exam. So same conditions, ozone, DMS. You would imagine you could cut through this double bond. There's a really easy way to do this. Keep your structure as similar to the ring as possible. Oops, let me make more room. Okay, so notice, actually I don't want to do that yet. Put the double bond where you used to see it. So we're here, put an oxygen, put an oxygen. You can either leave it like that, or you could expand it to the 1, 2, 3, 4, 5, 6, 7, 7. And that's the same. These are the equivalent. Okay, so those are two ways to draw that. Okay, so those are the oxidations. So osmium tetroxide and ozonolysis. There are two reductions, just one reduction. It's called catalytic reduction. So reaction 9. Oh, I'm sorry. There's one more oxidation. I knew I was missing something. This is epoxidation. Okay, so epoxidation is basically forming epoxide from an alkene. That's an epoxide, 3-membered ring with a center oxygen. So if I had a generic alkene, and I'm using MCPBA, or sometimes more specifically what we just call it peroxy acid, so it looks like a carboxylic acid with another oxygen. MCPBA is more specifically metachlorobenzoic benzoic acid, peroxy acid. So here That's that structure, metachloroperoxybenzoic acid. Okay, and mechanistically, this is another one of those concerted mechanisms where we're going to form an epoxide. So that would be a structure that looks like that. This is the result. So let's see an example of that. So if I did this, MCPBA, the result would be an epoxide that looks like that. So forget we could attack or approach from the front or the back face. So if we did that from the front face, it would look like that. If it came from the back face, it would look like this. Keep in mind, the left carbon is a chiral center, the right one is not. This is not a chiral center, there are 2 hydrogens. That's why there's no wedge dash orientation. I want to touch up on the last reduction. This, 10, sorry. Okay, so this is called catalytic hydrogenation. It is a reduction. Okay, and we don't cover a mechanism here, but if you had a generic alkene, H2 gas, and some sort of catalyst, we could see that catalyst be, platinum, palladium, or nickel. Any of those work. We essentially will have hydrogens add across the double bond. More specifically, these hydrogens add in a syn orientation. This is stereo-specific. Example of this. If we had a structure that looks like this, H2 and palladium, basically what happens is the H add in such a way that the nucleophile grabs the proton, and this sigma bond density comes back at the same time. If they approach at the same orientation, let's just say the dash, the back face, that would force the methyls on a wedge. Likewise, you have the other orientation. If they approach from the front, that would put the methyls on a dash. Okay, these are meso compounds, these are the same, so you would just expect to draw one of them. Okay, and that is a pretty good summary of all of your reactions. Good luck.